Hey guys, in this video we're going to talk about statistical significance and related concepts. So keep watching if you want to learn about confidence levels, test statistics, p-values, and how to interpret all of those guys. Let's start by talking about confidence levels. And we define the confidence level of our hypothesis test as 1 minus alpha. We've talked about alpha in our introduction to hypothesis testing video, and if you remember, it is defined as the probability of making a type 1 error, which is a false positive where we reject a good null. So a confidence level of a test typically varies between 90% and 99%, with another common value being 95%. And it depends on how much accuracy do we need from our test. So when we have the alpha of 5%, that means the confidence level for this test is 95%, and the area shaded in yellow is the area for an upper tail test, where we suspect that the mean that we are actually getting is going to be higher than the mean that is claimed by the null hypothesis. Whereas the same would work for the lower tail test, except for the alpha with the 5% would be in the left tail of our distribution. And the third possible case is if we believe that the mean does not equal to the mean under the null hypothesis. And in that case, we're performing a two-tail test where our alpha is split into two parts. One goes into the left tail and the other goes into the right tail, because the only thing that matters is that there's a deviation from the mean, and it doesn't matter in which direction it goes. Now let's talk about test statistics. So essentially what a test statistic is a single number. And this number, it takes the distribution of our data and then compares that to the distribution predicted under the null hypothesis and tells us how much those two are actually alike, or how far apart they are. So in case of the test of the means, such as the z-test or the t-test, it will take the mean under the null hypothesis and our sample mean and tell us whether or not they're actually equal. There are two main types of statistical tests, and more often than not, we're dealing with parametric tests. Those tests make assumptions about the underlying distribution of a population, and most commonly it's that the population is normally distributed. However, there are also non-parametric tests, and while they do not require your underlying population to be normally distributed, you are paying the price in the lower power of the tests. And examples of parametric tests would be the z-test, the t-test, the one-way ANOVA, or the analysis of variance, and the person correlation tests, while the non-parametric counterparts would be the chi-square test, the Mann-Whitney test, the Kruskal-Wallis test, and the Friedman's analysis of variance, which is different from the one-way analysis of variance. Now we'll finally talk about p-value. And this concept is of paramount importance. I think I'll also make a video on p-hacking in science, because this thing here gets abused pretty hard by people who want to make their research more significant than it actually is. Of course, because they spend time on it and they want to get published, but that does lead to some nasty consequences in the scientific community. For now, though, let's just examine what p-value is. And essentially, p-value is the probability of getting results at least as far from the null as observed, assuming that the null hypothesis is true. So you can think of it as a conditional probability. We assume the null to be true, and we're trying to see how likely it is that we will get the test results which are at least as far from it. And the key takeaway is that the smaller the p-value is, the more significant the result, because when we have a very small p-value, that means that there's very little chance that we could really get the test results we're getting if our null hypothesis were true. So let's say we conduct the z-test, t-test, analysis of variance, what have you, and we obtain the test statistic. So we get the z-score, t-score, or f-value, etc. And when we have our score, our test statistic, we are going to either look up in a table or we're going to calculate, and we have to obtain the corresponding p-value. So for every test statistics, there's a corresponding p-value. Now, another important thing that we need in order to interpret the test values would be the critical value. Now, you already know what alpha is, so for every alpha, you have to understand that there is a critical value that serves as the cutoff point, where alpha would be the probability under the curve that's bound by the critical value and the tail of our distribution, as you can see in the first image. And there are two main ways for us to interpret the test results and draw conclusions about our hypothesis test. So first, we may compare alpha to the p-value, and second, we may compare the test statistic to the critical value. So you can see that in the second image, there's the critical value and there's the test statistic, which is actually higher than the critical value. So in that case, if our test statistic is higher than the critical value, then we are able to reject the null. And similarly, the higher the test statistic, the smaller the p-value. So if the p-value is actually smaller than alpha, we also get to reject the null. So keep in mind those two different ways of interpreting the values, because right now we're going to take a look at a few examples. So first we have this problem here where we are given the alpha. We know that it's an upper tail test, so you can think back to that image we had in the first slide where there was a 5% alpha in the right tail of our distribution. That would be it. And we're given the z-score of 1.82. And the question is, can we reject the null hypothesis? First, we'll take the alpha of 0.05 and look into the z-table to find the corresponding critical value. And the z for our alpha is 1.64. So using the test statistic approach, we can say that our z-score is higher than the critical value, which means that we can reject the null. Now, if we use the p-value approach, we would instead do the opposite. We would go into the z-table and find the corresponding p-value for our z, and the p for our z-score is 0.034, which is less than our alpha of 0.05. So in both cases, we have enough evidence to reject the null. To understand the second example, you need to understand what a one-sample t-test is, and in case you don't, I recommend that you watch a video on our channel that I've made specifically dedicated to this topic. So if you're clear, then let's get started. We have the confidence level of 95%. We know that it's a two-tailed test. We are given the t-value of 1.41, and we know that there are 20 degrees of freedom, and we are asked whether or not we can reject the null here. So again, we could have used two approaches, the p-value approach and the test statistic approach, but for the purpose of accuracy, because we can really nail the critical value down to two significant figures with the t-table, I'll go with the test statistic approach. So we first calculate our alpha, which equals to 0.05, and then we divide that by 2 since it's a two-tailed test, and we get 0.025. So now we have to look into the t-table and find the critical value for 0.025. And such a value exists, and it's 2.086. Now we can see that 2.086 is obviously larger than 1.41. And that means that our t critical value is higher than our t-score, and that unfortunately tells us that there's not enough evidence to reject the null. Thank you very much for watching. Hopefully you found the video useful. If you did, please give us a thumbs up, and do not forget to subscribe for more mathematics videos.